The basis of an Atwood machine has two masses, both suspended by a string, and at the top of the string there's a pulley. This pulley is frictionless, so the string can glide freely within it. These two masses we'll call M1 and M2. The forces acting upon these masses are T due to the string, and then the force of gravity due to the object's mass. A F net equation for this object would look like F net equals Fg minus the force that opposes it, tension. And in an Atwood machine, the tension of both of the masses are equal to each other. So this tension is equal to this tension. What if we had a problem where the mass of M1 was equal to the mass of M2? Well, we can start with the F net problem. So for M1, the force of tension is acting upwards, and then force of gravity is acting downwards. The same can be said for M2. Tension pushing upwards, and then force of gravity pushing downwards. And remember, these tensions are equal to each other. So we first need to solve for T, because once we can get T, we can substitute it in for the other equation, because these T's are equal. So let's start with the F net equation for M1. F net equals, let's say the object's motion is this way. What's acting in that way? Tension. And what is opposing it? Fg. So it'd be positive T and negative Fg. And then these all can be substituted for M mass 1 times acceleration equals T minus mass 1 times the acceleration of gravity. And then if we solve it for T, we could say that T equals M1A minus M1G. Now we can use this T to plug it in for a new problem. So let's solve for the F net of M2. F net equals, the force of motion is this way, what's acting that way? Mg. So it'd be Mg Fg minus T. So Ma is equal to M2 times the acceleration of gravity minus tension. And we can plug in this where tension is, and we would get mass times acceleration equals mass 2 g minus this whole strand, minus M1A minus M1G. And then let's get all of our accelerations on one side and all of our gravity on this side. So we just have to move this one to the other side. So we'll get M1 times acceleration plus M2 times acceleration is equal to negative M1 times gravity plus M2 times gravity. And for each of these we can just pull out a variable. For this first one, we can pull out A times M1 plus M2. And for the second one, we can pull out G times negative M1 plus M2. And then if we want to solve for acceleration, we would divide each side by M1 plus M2. So that would be A equals G. Then on top we would have M1 plus M2 divided by M1 plus M2. So our formula is acceleration equals gravity multiplied negative M1 plus M2 over M1 plus M2. So this is the formula we would use for acceleration. Now if we go back to here, we said that m1 is equal to m2. So let's plug in some values for that. So in our initial problem, we had m1 equal to m2. So let's say m1 is equal to 10 kilograms and m2 is also equal to 10 kilograms. Then we just need to plug these numbers into the formula. So acceleration, which is what we're finding, equals gravity, force of gravity, times negative m1, 10, plus m2, also 10, over m1 plus m2, 10 plus 10. And that gives us acceleration equals 10, force of gravity, multiplied by negative 10 plus 10, that's 0, plus over 20. And if you fill all of this out, you would get acceleration equals 10 times 0, which is just 0. Acceleration equals 0. So if both masses are equal to each other, the acceleration would be 0. Here we have two masses of equal value. If our calculations were correct, when they're released, the acceleration should be 0. Now initially, both of these masses equaled 10 kilograms. But what happens if we move this weight to this side? So m1 would now have 20 kilograms, and m2 would have 0. So let's plug that in. Acceleration equals force of gravity multiplied by negative m1, that's negative 20, plus m2, that's 0, all over m1 plus m2, that's 20. That equals out to acceleration equals gravity times negative 1. Gravity is 10, so 10 times negative 1 is acceleration equals negative 10. Now when we set up this formula, we set it as the mass moving this way. So if the acceleration is negative 10, that means it's accelerating this way. So that means m1 would fall. And that makes sense because m1 would be the one that accelerates due to having more mass on its side. Now we saw when mass 1 equals 20 kilograms and mass 2 equaled 0 kilograms, the acceleration equaled negative 10. But what if we increase both of these by 20 kilograms? M1 would equal 40 kilograms, and M2 would equal 20 kilograms. So would the acceleration be the same, or would it be different? Well, let's plug it into the formula. Acceleration equals force of gravity multiplied by negative m1, that's negative 40, plus m2, 20, all over m1 plus m2, 60. So acceleration equals force of gravity, negative 40 plus 20 is 20, over 60. 20 over 60 is 1/3 times 10, negative 1/3 times 10, and that equates to negative 3.3 repeating. So even though the difference in mass stayed the same, the acceleration decreased due to m2 having some mass. And that is because in this bottom portion, we add them together. So when the masses increase, it's going to be a smaller acceleration. Now this acceleration applies to m2 and m1. m2 has an acceleration of negative 3.3 repeating, and so does m1, all in this direction. And that's because they are part of the same system. It wouldn't make sense for m1 to start accelerating and m2 to stay where it is, because that would mean the string would have to snap. They're part of the same system, so they have the same acceleration. Now we're going to do a lot more experimenting on a Atwood machine and how different masses can affect this system in different ways. The purpose is to know the acceleration and how different masses can affect it, whether they're the same or the differences increase or decrease. The goal is to determine a relationship between the masses on the Atwood machine and acceleration. And the materials we need is a lab quest, a vernier photo gate, a pulley attachment, a mass sets, and a string. String is used here to hold up the masses. Mass sets are used to cause the mass. The pulley is this. It's what delivers the string across. Vernier is a way to measure the acceleration of a string. And then the lab quest is used to calculate the string's acceleration and velocity. In the first experiment, we will change the difference in mass, but keep the total mass the same. Our first step is to set up the Atwood machine as described with the pulley system with the string attached. Our second step is to connect the photo gate to the lab quest. Our third step is to then set up a lab quest with a string that runs in a groove. Our fourth step is to gather enough masses totaling 100 grams from mass 1 and 80 grams from mass 2. For our fifth step, in order to measure the acceleration, we need to start data collection on the lab quest and display the velocity versus time graph. The slope represents the acceleration of the masses. For our sixth step, we will use the linear curve fit to find the acceleration of the lab quest. In this experiment, we will first start with M1 equaling 100 grams and M2 equaling 80 grams. We will slowly take away 10 grams from M2 and add it to M1 to find the difference in acceleration when we change the mass difference. Then, for our second experiment, we will find what happens when the difference between masses stays the same, but the total amount of mass doesn't. M1 will start with 40 grams, and M2 will start with 20. Every trial, we will add 20 grams to both masses. We will do 5 trials in total, and 3 trials per mass to minimize scientific error. Now, after all the trials we did, here was our results. In the first experiment, what we did was we increased the mass of M1 by 10 each trial and decreased the mass of M2 by 10 each trial. And what we saw was that as the difference in mass increased, so did the acceleration, even if the total of mass stayed the same. Now, in an Atwood machine, that makes sense, because if something weighs less, there's going to be more force pushing here. And the greater that force is, the more push there will be. Now let's graph some of our data. In the first experiment, our independent variable was the difference in mass. So that will go on the bottom, the difference of mass. And then our y-axis will be the acceleration. Now with our points plotted, we can see that this is roughly a linear line, which means the difference of mass between M1 and M2 causes a linear relationship with acceleration. In this experiment, we will be keeping the difference between masses the same, but change the total mass.
I didn't say that. Did I say short, fat, it's not funny? No, the Lucas one came, I know the it literally says
But in our second experiment, we kept the difference in mass the same, and the only difference was the total in mass. So we started with M1 equaling 40 grams and M2 equaling 20 grams. And each time we increased the mass by 20 of each thing, we kept the difference the same. So the difference was the same in each of these, but the acceleration was still increasing. Now why does that happen? Now the reason for that is because of our formula for acceleration. M1 minus M2, that is the difference in mass between M1 and M2. And this top number was always staying the same. It was always 20. But this bottom number, it was increasing when the total mass increased. So this was constantly 20, and this was always increasing. Now if our denominator is bigger, then that will decrease the acceleration. And that's what we saw for this. As the total mass increased, the acceleration also decreased because the difference in mass was not also increasing. Now with our second experiment, our independent variable was the total mass we used. And then we were measuring the acceleration. Now if we plug in all of our points, we can see that this has a quadratically sloped downwards. This means that the relationship between acceleration and the total mass is not linear. So in order to find slope, we have to linearize it. And once we do so, we end up with y equals negative 0.02 x plus b. This negative 0.02, that's the linear slope of this line. With this experiment, we learned how the difference of mass between m1 and m2 can affect the acceleration of this system. We also learned how to calculate and derive the formula for acceleration in an Atwood problem. We also found the relationship between acceleration and total mass, and the relationship between acceleration and difference of mass.
My bad.
What happened?
It broke. I put too much weight on it.